Good morning. My name is Randy Stott and I'm the managing editor of Gear Technology. Welcome to our session of Ask the Expert Live. Today we're going to be talking about gear inspection. I welcome any questions from the audience, so please feel free to sit down, come on in, ask these guys anything you want about gear inspection. Otherwise, I have some questions from the readers that I'm going to be asking them as well. But first, before we get started, I'd like each of these gentlemen to introduce themselves and tell us a little bit about themselves. And we'll start here with Mariano.
Very good. Hello, my name is Mariano Marks. I'm the product specialist in gear metrology for Wenzel America in Wixom, Michigan. I began my career at Carl Zeiss, where I trained the software and ran CMMs, and now I inspect gears and tooling, train and do presentations and demonstrations with our dedicated gear inspections machines and CMM solutions.
Dr. Mueller?
My name is Hartmuth Mueller. I'm 27 years now in the gear business. I'm working for Klingelnberg, and my actual position is I'm head of technology and innovation.
I'm Bill Mueller with Kapp-Niles. Career going back about 40 years, and every position I've had has been in operating and selling and helping with metrology, from MOG to Huffler to Gleason, and now Kapp-Niles metrology.
Very good. Thank you, gentlemen. I'm going to get started with one of the questions from the readers, and it's this one here. Is gear inspection on the shop floor practical? Is it reliable and fast enough to eliminate the inspection lab? And is it reliable and fast enough to eliminate composite tooth checking on a roll tester? Who wants to take that one on?
No.
Yes.
Maybe.
Okay.
There's from the engineering background, it's always a question with a depends.
Mm-hmm.
It depends. Of course, it depends on the quality of the gear. It depends on the type of gear, the type of machine, and most importantly, the type of environment. But in general, yes, because of today's technology with the thermal compensation, computer-aided accuracy, alignment to gear axis, all those things are enabling measurement on the shop floor. But it doesn't eliminate the double flank roll test, it doesn't eliminate the lab. So there's the two-sided answer.
Well, from my point of view, inspection on the shop floor is possible if the measuring machines are capable to run under these environmental conditions. This means you need to have isolation in terms of vibration of the shop floor, and you need to have a thermostable and a thermoneutral machine. This means that the machine does not grow because you have a large temperature variation in your shop floor, and the only possibility to get reasonable results is that the machine always has the same accuracy from a range of, let's say, 15 to 35 degrees centigrades. On the other side, you also need to take into account that the temperature of the workpiece is very important, so you need to inspect the temperature of the workpiece, and we need to live with the assumption that we have a homogeneous distribution of the temperature in the workpiece. If this is not given, shop floor measurement will not work. But the beauty of shop floor measurement is that you get very short cycles, so you don't need to run into the inspection room, you don't need to wait half an hour. Our idea is that the operator of the cutting machine or the grinding machine himself will inspect the gear by an inspection machine which is very close to the production machine. Mm-hmm. The other thing, the second part of the question, a roll test for contact pattern is critical. You can't do this only by deriving the measurement values from the inspection machine, because the measurement values from inspection machine, these are just lines or individual points, and on a roll test you inspect the complete surface. This is a much higher level of information.
I was going to say, it depends on the condition, how you define shop floor, right? But in today's day, you can add, vibration minimizing feet on your machine or something like that to minimize from forklift going on your shop floor, or depends on the quality of what you define shop floor. So I think you guys pretty much said it all.
Very good. Everybody in the audience, please feel free to come forward and have a seat, ask some questions. These experts are here for you. The topic is gear inspection, so come on down.
You see, we have Steve Bannon in the audience. Thank you for coming.
Next question from the readers is, how are recent advances in alternative inspection techniques, such as laser, X-ray diffraction, optical, and Barkhausen inspection, helping gear manufacturers in high-volume operations? Anyone?
I think the accuracy for tactile probes is still pretty well defined and more accurate, I think, than most optical solutions. I think we're starting to see it more and more, but I think you have to consider some interference effects, especially with a tooth shaped like a gear tooth, where you could have multiple refractions or reflections from a triangulation sensor that has a laser or something like that. Barkhausen, I think it's pretty implemented now on most gear inspection machines, and is something that I'm seeing more and more out there, I think.
I'd say with as at the advent of this technology, it's a way to collect a humongous cloud of data of the entire tooth surface on 360 degrees, which gives you a rough idea of the gear condition in a very short time. The gear specifications, though, are not such that they are aligning with this type of technology yet. So this is perhaps a good alternative for determining the condition of establishing an unknown gear, giving a very rough idea of the accuracy on maybe the 10 micron level.
Well, I have a slightly different opinion. If you have a tactile probe, the beauty of the tactile probe is you can move it in this direction, this, or in this. So you are completely independent from the direction. This means from your normal vector. If you have an optical system, you always have a preferred direction where to measure. Best situation is if you are perpendicular to the surface. This is for a gear just impossible, except the root. But the root is not that doesn't have these tight tolerances. Nevertheless, I think in near future we will have to live with multi-sensor probing for gears, because there are some advantages of the optical systems. And the big advantage of the optical system is the speed. We still have to improve the accuracy, but I'm very sure in near future tactile combined with optical system will be state of the art for gear measurement. And all other things like the Barkhausen thing, this is not related to the geometry. This is purely related to the material characteristics, for example, for detection of grinder burns. And Barkhausen noise is state of the art, at least for cylindrical gears. For bevel gears, it's a bit more complicated because the sensor, well, the misery with bevel gears is that you have a change of profile along the face with it. That makes it more complicated.
Very good, thank you guys. Next question is, how does a closed loop system help with gear development?
Well, a closed loop system, before we talk a closed loop system, we need to be sure that we have a producible geometry of our cylindrical gear. And this is not state of the art. Sorry that I have to pronounce this so clearly, but if a gear engineer designs a gear and he wants to have a certain flank form modification, he usually doesn't take into account the geometry of his dressing roll. He doesn't take into account, is it a 1-start threaded grinding wheel, 3-start, 5-start, 7-start? So he says, that's what I want to have, and the guy on the shop floor, he needs to come as close as possible. Before we talk about the closed loop approach, we need to talk about a producible geometry that must be derived out of the purely functionally orientated geometry. And as soon as we have a producible geometry, then we can separate the desired flank form modifications from the machining imperfections. And the only thing that closed loop systems are allowed to do, or what they shall do, is they shall minimize the machining errors, the machining imperfections. And if this is given, a closed loop system really helps the operator, because then we have a complete shift in responsibility. At the moment, the guy sitting on or operating the grinding machine is in charge of making good gears. If the guy on the grinding machine is just in charge of producing, of manufacturing the producible geometry, and then if the gear is not okay, it's the gear engineer who is in charge to make an improvement. I think that's the way for the future.
I think for bevel gears, it's pretty well defined for now, and the cylindrical gears, then another challenge. Things like a GDE, gear data exchange, is also coming about, I think, and helping with this completing the measurement process and helping to simplify it, I think.
The calculations from a measuring machine to correct the machining, whether it be a hobbing machine or a grinding machine, is nothing revolutionary that's been around for 25, 30 years. As far as decreasing the setup time and development, at the Kapp-Niles group, we've had onboard measurement being very, very effective at correcting for profile angle, correct for profile modifications, correct for lead crown for over 25 years. That's the most efficient, the quickest way to help the operator achieve the necessary quality. That measurement can be calibrated within a few microns of the value from the lab. So it's well within the tolerance of most master gears, or let's say class 4 gears. Nevertheless, as we approach the next generation with less skill, these will be much more important. And I think still the onboard method is still the most direct way. So you have a measuring system on each machine.
A little bit more complicated in future. If we think about topological grinding, then you can't live with FH alpha, FH beta, C alpha, C beta. These parameters will not help you to describe what's really happening on the flank, if on a topologically modified flank. Therefore, we need to have a theoretical base. We need to have theoretical nominals, like we did it, like we have it for decades now for bevel gears. And I think that's the way cylindrical gears will have to go.
Why isn't that possible on a grinding machine?
Well, it's not possible on a grinding machine because worldwide there are no perpendicular axes. And if you inspect on a grinding machine, and if the axis is not exactly parallel, you measure with the same axis like your machine, so you get a nice result. And if you compare this to a measuring machine, then you have a difference. So this
absolutely the lead angle and the index cannot be qualified on the machine, but the tooth twist and the flank modifications can.
This can be.
Okay.
Are there any questions from the audience? Very good. Next one I have is, how often should my gear inspection system be calibrated? And what about my master gears, gauges, and other artifacts? And when do I need third-party certification?
Rather simple answer. What your certification process needs. If you are certified according to ISO, there are fixed dates when you need to make a calibration. So that's nothing to discuss about from my point of view.
Well, I can elaborate a little bit. In the old days when you had analog probes, you really needed to calibrate the probe. Every time you change the probe, every time you change the temperature of the part or the lab, to make sure that your deflections were correlating with the digital values on the chart. Today we're using all digital probes, so that's not such a necessary calibration. It's simply a matter of center find. So going back to the sphere is a very, very short and simple operation which can find the reference center line of the machine and the part. Most customers determine how often they need third-party calibration. It's through their quality manual. Well, they have to comply with their quality manual. Generally, it's once per year. It's phenomenal business for the measuring machine companies. But it needs preventive maintenance, and that's the big benefit is going in to make sure there's no damage to the machine, make sure the operators are using it properly, and gain a close connection with the customer. That's when you need the third party, and it's mostly customer driven.
I was about to say once a year is an average when our machines are calibrated. And as far as third party, I think we have a certification process where third parties can get certified through us, through Wenzel, and that's the only way that the customer is able to take care of their machine if they need to, if they want to choose somebody else.
I took third party to mean the manufacturer.
Yeah.
Oh, okay.
I don't have any
Either way.
more information. So.
Okay, third
also
party
my
is when
understanding.
you don't have any service engineers at Wenzel.
Yeah.
Then you need a third party.
Right, or they're closer to the customer or something like that, right? But I was also going to tie it with, as far as servicing the machine with Industry 4.0, we're now starting to gather information from the controller, for example, to see when and where the machine needs to be, when it's wearing out, and if when it's going to maybe need some maintenance, depending on how you use it, when you use it, and what the operator is doing, so we can collect that information and get ahead of that, really. So.
Okay, I'm going to tap into some gear basics here, and the next question is, what is the difference between single flank and double flank inspection?
Okay, this refers to composite checking with a master gear. Again, the composite check is necessary so that all surfaces of every tooth is checked. And this can be done with either double flank or single flank. So if you're looking for gross errors and PD runout, the double flank is typically used. You can also determine through evaluation of that trace whether it's a short wave or a long wave error, meaning it could be in the individual tooth mesh region or even one tooth. The single flank test is a test with a fixed center line, whereas a double flank test is a test with a varying center line with no backlash. So the single flank test tests actual transmission error. So it's a more direct test of how the gear should function, but it's also much more expensive and complicated to implement.
Yeah.
I agree completely. The single flank test tells you something about the running behavior of the gear, whereas the double flank test is mainly used to detect nicks and burrs and runouts, things like that.
Yeah, single flank, fixed distance, I think for transmission error, can we boil it down to that? And then double flank, you have the influences of run out and healing, a bunch of different deviations, whereas the GMM really only usually touches at one point, and it's not an apples to oranges comparison, but so yeah, they both have their pros and cons. But yeah.
Very good. Thanks, guys. I'm going to move on to big gears now, and the question is, what are the latest technological advances for the inspection of large diameter gears?
A big CMM or a big gear GMM. Yeah, we can inspect up to 4 meters, I believe, and it's all about getting the part right on the machine, safety, and other than that, I think it's pretty much the same. But
Well, I think with big gears, onboard inspection makes more and more sense, because moving a big gear from a machine, from a gear cutting machine or a gear grinding machine to an inspection machine takes how many hours? 5, 6, 7 hours. So in this case, onboard inspection really makes sense. Nevertheless, if you want to have a certified gear, or if you need to deliver a certified gear, then you need to go on a large CMM, on a large gear inspection machine. No way around.
Yeah, several things have driven the demand for large gear inspection, and up until about 5 years ago, the largest machine that was ever made was 5 meters, never ran, and so a new technology was introduced by our company to enable direct drive technology with hydrostatic work spindle, similar to a grinding machine, but it's able to produce incredible accuracy with this technology and carry 40, 50, 60 tons workpiece sizes. So it's possible to measure on board, but our experience on the grinding machines is you have to follow the discipline that someone in a lab would follow in order to get a reliable result off the machine, and that is frequently overlooked. And so there can be undiscovered errors, which on a large gear can be catastrophic. So as the technology now is available for very reliable and accurate large gear checkers, more and more companies are choosing that rather than taking the risk of onboard measurement.
Very good, thank you. My next question is, when is it better to purchase a dedicated gear inspection system as opposed to inspecting our gears on a CMM? In other words, what can my CMM not do for me?
I break it down like this. It depends on what you're making. If you, for example, have 90% gears and 10% other parts, then maybe a dedicated gear inspection machine is best for you. If it's 50-50 maybe, then you do one of each, so you have a machine that can do, they're good at each of what they do. Then you don't have to worry as much about throughput. If you do 90 parts, 10% gears, maybe you get a CMM solution with a rotary table, and that's a wholesome solution as well. And as far as what you get in GMM, you can get a tailstock, although there are CMMs with tailstocks as well, and also easier part loading. I think with the GMM you can just set it right there on the rotary table. So,
well, that's fully right. I just want to add, with this, if you have a CMM, you need to. This is very sensitive to the environmental conditions. So you need to have a climate-controlled cabinet where you have your CMM. And if you think to inspection on the shop floor, this is only possible with a gear measurement machine, not with a CMM. And another big difference is that a gear measurement machine is usually significantly faster in gear inspection than a CMM. It's not a question of accuracy, it's just a question of time you need for inspection.
Yeah, the advantage of the GMM is speed, size, and price. You know, many years ago, many people think, well, with a CMM I can do both. I don't need to have a dedication, but I agree. If once you get to a point where you have to wait for a gear inspection result because the CMM's checking a housing, you're not running production. And the gear grinding machine is more expensive than the milling machine. So you better get a gear checker. I had a customer invite me in to do some consulting, and he said, how can I improve the throughput on my gear grinding department? And I said, you need more measuring machines because your machines are sitting down 2 hours every shift waiting for a measurement. And they bought 3 more measuring machines, and that solved the problem. So it's a small price.
yeah, I think the main is the speed factor for CMM versus GMM is usually the probe changers. If you have a big CMM, just has to take a long. You're working with a larger volume as opposed to smaller volume. So that's all I wanted to add to that.
All right. My next question is, to what extent can my gear inspection processes be automated? Who wants to tackle?
I think in theory everything is there for it to be automated. Just automatic chuck, PLC controls, and you can set your GMM in a booth and take off. Yeah, not sure.
Well, I think the main challenge is not just the automation of a gear inspection machine. This can be done. We have several machines which are completely automated. But what is the purpose of measuring? From my point of view, the purpose of measuring is, first of all, to get a clear announcement about your quality, and the second is, if you are not well balanced with your quality parameters, to apply corrective settings. So if you have an automated process, you also need to have automation in closed loop process control. That would be the logical next step.
Over the years, I've watched the measuring and the gear analysis software be increased in sophistication to an incredible value, and yet if you tour 80% of the gear labs, you find that they're using it as a go, no-go gauge. It's either in or there's a red line or a red number.
Yeah.
And so the value of putting it on the floor is a go, no-go gauge. You simply raise a flag when there's a red output, and the rest is for documentation purposes. And it is, like you said, it's nothing There's not much required, a simple interface. Everything's automated as it is. And being on the floor is just a case of having someone occasionally verify the calibration.
Well, yeah, that's right. But I think there are also some conditions that need to be fulfilled for when we talk about automation. This means you need to identify your parts automatically.
Right.
Without a DMC code or an RFID chip, it's not possible to talk about automation, because bringing a measuring machine after each hard finishing machine, that would be nice for us, but that's not feasible. So you will have a chaotic part flow to the measuring machine, and there you need to detect which part do I now have to check. So there are some constraints that need to be fulfilled from the customer side.
Yeah.
Yeah, it gets very complex when you have one measuring machine trying to control multiple production machines.
Yeah.
Thank you, guys. With the increasing quality requirements of gears, how close are we to the limits of inspection capability?
Well, rather close.
Yeah, we're at that point, have been for many years, and it keeps challenging. If you follow the AIAG standards for GR&R calculations, you rarely will find that it meets the 10% rule. You're lucky if it's 20%. I was on the Hob Tool Committee of HMA for many years, and as they defined the tolerances, getting smaller and smaller and more classes, and the steps in the tolerances were in the sub-micron level, and finally someone raised their hand and says, is this, can we discern this on a measuring machine? And everyone looked around and says, no. Well, then what's the point of creating all those different classes? So obviously it's made big improvements, but it's still, as soon as the gear measuring machine moves forward, the tolerances follow.
I fully agree. We come closer and closer to the capability limit of a measuring machine. If you think, for example, to noise-relevant effects on the flanks, these noise-relevant effects, they are in the range of 100 to 300 nanometers. And if you follow the GR&R studies, then you would need to have a measuring uncertainty of 10 nanometers. Forget
Today,
about this. This is not possible.
Even in a lab, if you look at the uncertainty from a certified lab, an AL2A 1725, it'll say 2 microns, uncertainty in the profile measurement. Then you add that to your differences on your shop floor between one machine and the other, in the lab even. And we found that, especially with, you talk about closed loop systems, you have the potential of destabilizing the machining process just from the measuring deviations. So you're one time changing a plus, then a minus, and if you look at the long-term capability of the machining process, it becomes less stable with closed loop feedback. That's our concern.
Yeah, I'm fully with you with this concern. On the other side, this is also a limitation for optical systems, because we come closer and closer to the sub-micron area, and this is nearly not possible with optical systems. At least not repeatable.
Yeah.
That's what I was going to say, is optical systems have to make that much more of a leap forward for this to come through. But other than that, I agree with my colleagues.
Nevertheless, they will come.
I have a rule, advise everyone, if you get a report from the lab and there's a red mark that it's out of tolerance, so many manufacturing people run out to the maintenance department or run to their supervisor or run to the engineer and say, what do I do? They shut down the machine. And I say, turn around and go back to the lab and tell that guy to measure it again, and then ask him to calibrate it for you. And stand there and watch him. The guy running the grinding machine, which is $1 million machine, is the boss. Take control.
That's a real pragmatic approach, which I would like to follow.
With that in mind, how is today's equipment able to verify the increasingly demanding surface roughness requirements of gears?
There's, I think as long as you can get in the tooth, I've seen GMMs that you can apply the roughness sensors in there. CMMs now are developing it, very advanced too, to be able to just get into the part, I think. Yeah.
Well, I think It's not. It's a pretty complicated area we're touching now. A lot of surface improvement was done to improve the gear efficiency. This means you have a better micro-pitting safety, and you lose the micro-pitting safety by using a thinner oil, and this gives you a significantly better efficiency in your gearbox. But I think we are now at the limit that, at least from my perspective, we should discuss about the standards, how to measure roughness. We just measure roughness by one line. We have on our machines, we have this roughness sensor, works perfectly, absolutely repeatable, but is this the right way? Mm-hmm. Because the gear engineers, they always say, well, if I have a better roughness, my gear will perform better. Yes, but at the end, we need to have not just a line inspection for the roughness, we should take into account the complete area. Yeah. This means we need to have an area inspection, and there I see a huge advantage in optical measuring systems. Mm-hmm. Because it does not count whether the surface is 2 microns before me or 2 microns behind me. If I see the roughness structure, the complete structure of the surface, this will be an improvement, and there I see a big advantage using optical systems.
I agree. It's an area of rapidly increasing interest. There are many more parameters available to the engineer to specify the roughness, and collecting the data it's relatively easy to put the probe on the machine and collect the data and analyze it. It's a question of whether it actually correlates with a value from a dedicated surface finish tester, which has a much lighter force. If you're dragging a very small diamond across a gear surface and it's a 2 micron radius, you have the probe for gear measuring has a higher force than a surface finish tester, and so it actually modifies that surface. So if it's measured, it's not going to correlate with the surface finish tester. But as you say, you're only measuring one line, and the variables in the specification are still very much in flux. There's no standard as there is with DIN, ISO, and AGMA all converging to a common set of characteristic definitions. So,
but you can avoid this if you use a skid system. Then you have a real small force on your diamond needle.
Yeah,
but nevertheless,
and then you got the problem of the accessibility to get the skid into the SAP. Yeah. It's yeah.
So actually, there is a limit
also
of
the optical reaching the SAP.
Yeah.
So
I'm not sure what the force is on the dedicated roughness, but I think on other sensors it's about 50 millinewtons or something like that. So I don't know if that was.
The newer probes are available with a lighter force. Those are now in development and application use, and it does yield that overcoming that deficiency.
Okay.
Nevertheless, I think a surface roughness on a gear measuring machine makes much sense.
Oh,
if
sure.
I remember the old days with a perthermeter and some magnets, and what I did is I checked as long as until I was really in tolerance. And
yeah.
The big advantage of a GMM is that you have a repeatable and a reliable surface roughness measurement.
Yeah.
That's one of the biggest advantages.
And everything's in one report and all one.
On one sheet.
Now we're coming to the age where not only do they want a surface finish control, but they want different surface finishes at different areas of the tooth mesh. So it's getting even more interesting. Plenty of things to challenge us.
Yeah.
Very good, thank you.
A question?
I thought I heard a question.
Good.
If you do have a question, just raise your hand. I've got one more from the readers here. Why is pitch line runout considered a key quality measurement parameter when accumulated pitch error would appear to be a more qualitative functional attribute?
I don't know that that's a true statement. Pitch line runout is, in my opinion, only a characteristic to be used for pre-finishing control of the quality, so that you have equal stock removal in the final grind. Mm-hmm. Accumulated pitch, of course, is approximating what could end up being the transmission error.
I'm fully on your side. I think everything we're talking about gears, these are some artificial hypothetical things. What's a pitch line? The teeth doesn't know anything about the pitch line. The teeth knows only about the contact. And this is the big difference to 3D measurement tasks. What we do with gear measurement, we make a purely function-orientated measuring. So we follow the contact line with our touch probe, and then we know whether the gear will behave reasonable or not. So it's basically a completely different approach to measuring what we do with gears than in comparison to regular CMM measurements. And I think the pitch line measurement is just to have an equidistant stock for the hard finishing operation afterwards, for not more.
Yeah, agreed.
Very good. If there are no more questions, I would like to thank our experts. It's been a very educational session, so I appreciate it very much. Thanks, everyone.
Thank you.
Thank you. Thank you.